So why I brought the momentum here is trying to do the estimator. So originally, yeah, we spent some time about the moment and then moment generated function. But why I brought the moment here is trying to estimate our population parameter using sample, right? So this is first one is a method of moment. We call it a method of moment. It's estimator. How can you estimate the population parameter using sample based on the method of moment? So we will estimate our population parameters using sample data. Suppose the parameter is some, and maybe some distribution has a one parameter, some distribution has two parameter, three parameter, right? Let's say we have like a k parameters, right? And then you can tell the moment j's moment will be defined in this way, right? This is a j power to the j because it's a jth moment, and then this will be calculated that way. So this is just since this is expectation, so you calculate the integral my value times against our PDF. And then J's sample moment, this is a population. So this is for population. But this is for the sample. Sample is here. We have actually n number of sample. So how can I get a n number of sample is to just simply add up, because again this is the expected value of xi, right? And j. So I have to power to the j of each number and then calculate the expectation. So I just add up and then divide by n. That's the expectation, right? Because that's the expectation. I can calculate the moment, j's moment, using sample. So I have a discrete number. So you can just simply calculate the expected value of x power to the j. Now, method of moment estimator for the parameters is to find out the solution of all of this. So this is the what? This is the population. Moment. And this is the sample moment. So you set up all this is case, right? And then solution to the equation. So solution will be the theta, which is the parameter. So we're looking for the parameter that satisfies this system of equation. Why we have the k different equation? Because our parameter is has a k component. So altogether is the theta. Okay. So when we talk about the theoretical thing using alpha, theta, and then so it's not clear what we are doing here, right? So let's use in example. Method of moment in the Bernoulli case. Bernoulli is just a one trial, and then outcome will be just 2, 1 or 0, right? So let's say we have this is the sample, and I know it follow the Bernoulli distribution, but I don't know the p. So I'm just trying to estimate p using sample, n number of sample outcome. So we will have because our parameter is only one parameter, so we will have only one equation. So here the alpha 1, which is a population moment, will be same as, so population moment it will be the expected value of x, so it will be p, right? However, that should be the same as a 1 over sigma xi, because this is the first moment. That's why I don't power here is actually it's a power to the 1. Right? So it's clear our estimation of the p estimator for probability of success p will be just simply average of x, the sample data. So this is clear. Bernoulli says 0 or 1, so x1, x2, x3, and xn will be all 1 or 0, 1, 1, 0, 0, 1, 0, 1, right? So you tried n number of times, and then you add up. If you add up, what you will get? You will get only 1 plus 0 plus 1 plus 0, right? So the summation will be only number of success. So this is the 1 over n times sigma xi. So this part will be number of success, right? And this is what? N is what? N is the number of trial. So if you try like 10 times and then the number of success like becomes like a 6, then what would be the probability of success? So 60%, right? So this is 1 over 6. So if you have like a 1, 1, 0, 0, 0, 1, 0, 1, and then 0, 0, then you try 10 times, and then how many times did you success? 1, 2, 3, 4 times you are success, right? So if you just add up all this number, you will get all this number, you will get 4. And then what is the trial? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It was a 10 trial, so you divide by 10. So if you look at this sample data, what would be your estimate of probability of success will be 4 over 10 is 0.4. That's intuitively clear. However, we show what kind of logic behind simply count summation of all this number and divide by total number will be the estimator of the success probability. Because this, as you can see, actually we utilize the method of moment. Population moment should be the same as the sample moment. So we're trying to find out what kind of parameter will make a population parameter same as the sample population moment becomes same as the sample moment. This is the way how to do it. Method of moment in normal distribution. So if we have a same way, we have an n number of sample, and I know that's from the normal distribution, but I want to know what is the mu and what is the standard deviation. Then first moment, alpha 1 should be this is a population, right? Population side, this is a population side. It's more like a theoretical side. So alpha 1 moment, first moment is expected value of the x, which is a mu, and then alpha 2 will be the this way. This is a moment. Will be variance plus expected value of x square. So what is the variance? Variance is the sigma square. And what is the expected value of square is the mu square. But why this is this? If you recall the variance, of x equals expected value of x square minus expected value of x square, right? So this is our second momentum. So if you add expected value square both sides, then here it will be the variance minus expected value of x square will be the expected value of x square, right? So this is the moment. So this is the moment. This is the variance plus, because I have to add both sides plus this one, which is the mu square. So you can get a moment should be this way. Right? Now, by using this one, this should be, this should be same as what? Sample momentum. This is first order. Sample. This is a sample. First sample moment. So, what is the estimate of the mu will be the just summation of all x variable, sample variable divided by total number n. Again, this is the quite intuitive. How would you estimate the population mean? Is the sample mean should be the best estimator for the population mean. Again, it will give you the background logic why we can simply calculate the sample mean. That should be the best estimator. I mean, not best estimator. This is the according to the method of moment, that is the estimator for the population mean. And same way, this side is the what? Is the second moment, and then this is the what? This is the sample moment, second order. Right? So you can move, because I want to know the variance, so you can move this one, subtract the mu square both sides. And then what is the mu? I don't know the mu, but I can tell sample mean will be the best estimator of the mu, the mean. So you can just move that way. So originally it's a sigma square will be 1 over n sigma xi minus mu, which is the x bar. Yeah, we saw the second momentum. It's the right, and then so we just find out. We want to know the estimate of the variance. So that is the expected value of the second momentum minus mu square. Okay, now you can rewrite this is a 1 over n sigma x square. And about mu, so mu is actually the expected value of x. So mu square, it will be the expected value of x square. Let me rewrite this one instead of this one. So let's use x bar. Okay, so since this is the x bar is this is the sample mean. So this is x bar square. So now you wonder how this one becomes this one. This is what you can find in the slide, but actually the calculation follow is something here. So how can this one becomes this one? We wanna, instead of calculating this one, actually I will show you why this right hand side is equal to the left hand side. So I will expand this. First, this is a 1 over n and sigma. If you just expand it, this is the xi square minus 2xi x bar plus x bar square. Right? So if you take it out, this is the 1 over n, separate out, so xi square minus, if you just put it in, it's a 2 over n. Because the x bar is just fixed number, so you can treat this like a constant number. And then sigma xi, right? Plus, same thing, since this is just like a constant number, so you can handle this is just 1 over n sigma x bar square. Now you can rewrite it. This is the 1 over n sigma xi square minus what you can think is the 2 and x bar is here, but this divided by n and then together this one, what is this one? So sigma of xi divided by n is actually x bar, right? So this part is 2 times x bar times sigma xi divided by n. So this part is same as x bar, right? So that's why it's x bar times x bar. Plus, since x bar is just a constant number, so if you just summation x bar square n times, this will be the 1 over n times n x bar square, right? So this n and x cancel out. So you have a 2x bar square, this is minus 2x bar square, and this is just plus 1x bar, just like previously we saw. So this is the just sigma of xi square minus x bar square. So that's why, as you can see here, this is the same as this one, and then I show you from here to here, this is the same as this one. Okay? Okay, so therefore this calculation so this part going over here is 1 over n sigma, you just saw that, right? Is square minus mu square will be something like this. As you know, when you calculated the sample standard deviation, we usually use instead of n, we usually use n minus 1. This is the unbiased. So this is the biased. estimator. The reason is if we use this one as a mu, this is not biased. However, once we replace our mu with the x bar, this becomes biased. The reason is like that. When we select the sample, if we know the real mu, then if you calculate the distance and then square and add up, calculating the variance, it will be not biased, unbiased. So if we have a formula this way, is 1 over n sigma xi minus mu square, this is unbiased. But why we cannot use? Because I don't know what is mu. So only thing we can do is we replace this mu with the x bar, which is the estimate of the mu. When we replace x bar to the mu, because we don't know exact mu, so we will choose x bar somewhere. Then all the case, the distance will getting shorter. I will not talk about in the detail and why it should be the n-1. So when we replace to the mu to the x bar, this denominator n will be biased. So if we calculate it this way, it's n and then x bar, this is biased estimator. Okay.